Okay, welcome to today's lecture. First thing is we're going to talk about Lab 5 today. Not really cover any new material. We're going to review some things that are going to help with Lab 5 and go through the lab sheet, and then I'm going to give you some time to work on that. Also, as a reminder, you should get out and vote. If you haven't already, then see if you can figure out how to do that. You can do a Google search and find out where you need to go. And hopefully everybody takes that seriously. It's important to have your voice be heard and take part in the process and stand up for what's right and good and logical and reasonable. So get out there and vote. All right, anyway, let's dig into what we're going to cover today. So first off, today's lab, we're going to talk about Lab 5, which is what's called the game of life. So let's go ahead and take a look at that. So first off, it's a game that a mathematician invented called Conway, John Conway. And he actually was very influential in a lot of ways, just passed away this last year. But let's go ahead and take a look at the lab sheet, and then we're going to look at the game of life a little bit more and have a little bit of more explanation as to how it works. So let me first off switch over to the lab sheet. Okay, so here's a lab sheet. Let me zoom in on that so you can see that a little bit better. And let me see if I can adjust this so you can see it better. Maybe right about there. All right, so the first thing is, notice that the game of life, like we mentioned, was invented by John Conway a lot of years ago. What's that, 50 years ago now, 1970. And that's an example of what's called a zero-player game. In other words, you don't sit there and play it against an opponent. You don't even play it yourself. It kind of plays on its own. And it's actually a kind of a mathematical construct called the cellular automaton. And an automaton is kind of like a robot or a machine. So this is a machine that's built out of individual cells that interact with each other, kind of like a living organism. So the idea is the game consists of a two-dimensional world that extends, in this case, infinitely in all directions, divided into cells. Each cell is either dead or alive at some given generation. So in other words, it's kind of like cells of your body, that some of them spring into life, like skin cells. They eventually die, they fall off. It's like that, but we're dealing with these boxes in a grid, or cells in a grid. And the idea is that this game has a set of rules that govern how we get from the generation we're on to the next generation, and then from that generation to the next one, and from that one to the next one. And so the idea there is, if you think about one of those cells on a grid, every cell has 8 neighboring cells around it. So in other words, you have this 3x3 square. There are 8 cells around any given cell, and it's the number of neighbors in Conway's game of life that entirely determines what happens in the next step. So the rules that Conway set up for the original version of this are listed below. All right, so the idea here is, 1, if you have a live cell that has fewer than 2 neighbors, so in other words, if it has 0 neighbors or it has 1 neighbor, then that cell dies of loneliness. In other words, it's too isolated, it dies out. If you have a live cell that has more than 3 live neighbors, so if you have 4 or 5 or 6 or 7 or 8 neighbors, that one dies out from overcrowding. And if you have a live cell that has exactly 2 or 3 neighbors, it lives. So that covers all of the possibilities. Less than 2, 2 or 3, 3 or more. So that covers every possibility for a live cell. And then the rules for dead cells, if you have a dead cell that has exactly 3 live neighbors, then that cell springs to life. So in other words, there's enough space that has enough neighbors, it comes to life, has good conditions for that, it springs into existence. So in this lab, what we're going to be doing is we're going to be implementing this kind of two-dimensional version of that. And the one restriction we're going to make on Conway's version is he had kind of this infinite-sized kind of grid. We're going to have a finite-sized grid, and we're going to define that as being essentially 25 by 25, but we're going to use pound defines for that. So we could actually change this and recompile it and have it be a different size, any size we really wanted it to be. Obviously not infinite, because that's not possible with a finite computer system. But other than that, it's going to work just like that. Now, a couple things about the how the program needs to be set up. Let's start with the main program. The main program is, again, in C. That's where execution begins. So that's going to create this 2D board array that has board width by board height cells. And then we're going to call the init board function to initialize the board. And we're going to initialize it with 300 randomly chosen cells that are all set to be alive. We're going to run the game of life by calling the NextGeneration function once per cycle. And then for each cycle, it's going to display the board and then allow the user to press enter to continue to next generation, or type quit or exit or Q to terminate the program. So in other words, there's going to be a little while loop there that says generate the call the next generation function, display the board, get some input from the user. If they just hit enter, show the go back to the top of the loop, next generation, display board, get input again, enter again, and so you're going to be able to hit enter and cycle through, seeing each of the frames evolve. Now we're going to be printing this out in kind of an ASCII format for this lab, so we're not going to use graphics right now. We're going to use an asterisk for a living cell and a period for dead cells, so just a dot. So you'll be able to see the grid with the dots. You'll be able to see the asterisks coming to life, moving around, doing things. And then maybe everything would die out. Maybe things would reach some stable point. Maybe things would continue to move around. But that's what we're going to do. All right, now let's go through these functions one at a time. But what I want to do is, rather than read them off of this sheet, I'm going to go back to the presentation, and we're going to spend a little bit of time, and I'm going to give you some hints on those to make things a little bit easier for you. All right, so let's go back to the presentation. Okay, so back here at the presentation, let's talk about the game of life, so you make sure you understand what we're talking about here. Make sure you understand how it works. So the board consists of a grid of cells. Each cell is either alive, which in our array might be a 0 for dead, a 1 for alive. But when we print it out with a display board, it might look something like this. So here's a 5x5 board instead of a 25x25. But you'll notice it looks like this. We have this box. It's got either an asterisk, that's alive, dead, dead, alive, alive. So the board might look something like that. Now, the rules, as a reminder, are listed here. So a live cell with fewer than 2 live neighbors dies. A live cell with more than 3 live neighbors also dies. A live cell with exactly 2 or 3 lives. A dead cell with exactly 3 springs to life. So given our board down here, let's look at how this would go to the next generation. So if we were to go through and count up the number of neighbors and come up with a neighbor counts here. So for example, this first one here, how many neighbors does that have that are alive? In this case, there's 1, 2, and that's it. So there aren't any over here. They're up there, so it only has 2. So that would be 2. Let's go over to the next one. What would this one's neighbor count be? That one would be 1, 2, 3, 4. And the next one over is 3. So 1, 2, 3. And the next one over is 2. 1, 2. And the next one over is just 1. And then the next row, this one will be 1, 2. This one will be 1, 2, 3, 4. This one would be also 4, 1, 2, 3, 4. This one would be 1, 2, 3, 4, 5, 6. So here's what the neighbor counts would actually come out as if we were to go through and count up all the neighbors. Now, what we can do from there is now we can decide which ones need to stay alive, which ones need to die out, and which ones that were dead before need to come alive. So to do that, if we look at this one, for example, this one has exactly 2 neighbors, and it's already alive. So you notice that that fits a live cell with exactly 2 or 3 neighbors. So that one's going to stay alive. What about the second one over? That has 4 neighbors, but it's also dead, so that one's going to stay dead. The next one over here has 3 neighbors, so it's 3, and it is currently dead, so that one is going to spring to life. So the idea here is, what's that next generation going to look like? Well, here it is. I marked in green the ones that are going to come to life, in red the ones that are going to die out, either from loneliness, like this one with the 1, or ones that there are too many cells and they need to die out, like this one with 4, because notice this is, if it's a live cell with more than 3, that one was alive, but it had 4, so that one's going to die out. So the next generation is going to look like that, wherever we had the green. Now, That process would continue for every generation. So we'd go through this one, count up the neighbors for a cell, and then if it's alive, take this action. If it's dead, take a different action. And we would do that for every cell, for every row and column, and propagate this thing through time. Okay, so let's look at the functions for making this. So first one is a init board. And for the board, we're going to pass to the init board function a pointer to the board and the number, an integer number of how many we want to be alive. And then when we initialize the board, we're going to say, start it off with 300. So the board is going to be passed as a two-dimensional array. We'll circle back to that here in a little bit. The board array can be a 2D array of type char, so bytes, individual bytes for every one of the cells. So we'll talk more about that in a little bit too. And then num alive will be passed in as an integer. So this is just an integer for how many we want to be turned on, or alive at the beginning. Now, one question that's important to ask is how are you going to set random cells to being alive or dead? So for example, they need to be randomly chosen. So let's go back and look at the board again. So let's say we have this 5 by 5 grid. And let's say we wanted to add 10 cells that were alive. Well, here's what I would do. I would say pick a random row and a random column, or maybe I and J or X and Y, or however you want to think about it. And then we would basically go to that position. And if that position was dead, we would set it to alive and then increment our count saying, hey, I found one that was alive or that was dead. I turned it to alive, so that counts as 1. Or maybe I start at 300 and I count downward. So, or in this case, 10 and count downward. And say I found one, I can take that one off the list, decrement it. So whether you increment up to that number or start at that number and go downward, that's fine. Now, what if I pick a random number that's a cell that's already alive? Well, I can't count that one. I need to basically just try again. I need to say, well, that one was already had something, so let me go back and try generating a new set of random numbers. So the only time we want to count one as being alive is when it's empty, it's not currently alive, and then we're going to change it right then and then try again. Okay, so how do you generate random numbers? We talked about that in the past. You can go back and look at the lecture for that, but you're going to use the rand function, and you're going to probably use mod with that, modding it by the num rows, num columns, depending on which one of the indices you're generating. Okay, so that's the init board function. And notice since we're passing an integer or a pointer to that board in there along with that integer, that pointer to the board, that's going to allow that function. And notice this is not the complete function prototype. We need types on these things. I'll let you figure out how to do that. But you'll notice that with this init board function that we're passing a pointer, so this function can actually change the contents of that array because it has access directly to that array. Okay, display board. The display board function is just going to go through and print out the board array in some sort of text form. So you're going to use an asterisk for living cells, period for dead cells, and a couple hints for this one. Use nested loops to go through each cell of the array. In other words, you're going to go through every row, and then inside of that, you're going to go through every column. And then inside of that, you're going to have some kind of if statement that says, hey, if this array at this row in this column is equal to, I don't know, 0 for dead, then print a period, else print an asterisk. So one other thing is make sure to print the new line characters. So when you get to the end of a row, \n goes down to the next line, not /n, \n, and / is the one that's up on the above the enter, not the one that's on the question mark. So make sure to print that. And what you should see printed out would look something like this, but 25 by 25 instead of 5 by 5. Okay, the num neighbors function, when you call that, you're going to pass in a pointer to the board, and you're going to pass in an X and a Y, or you can think of this as a column and a row, however you want to think about it, but X and Y. And what that function is going to do, it's going to return the number of live neighbors around this cell. So, since our world is finite, if a cell is next to an edge, meaning all the way against, in let's say column 0, or in row 0, or in the column that's all the way on the right, or in the row that's all the way on the bottom, if it's in one of those, then we cannot look at the cells after that or outside of the range of the thing. So in other words, we need to make sure that we handle that case. All right, a few hints for this one. The function's going to return a number, and there should be an underscore there. Apparently the word processor decided I do not need that. Okay, so the question here is, what type of number is that? Well, it doesn't need to be a float because it's going to be an integer count. It'll be either 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8. That's it. So this is going to need a return type. And think of neighbors as offsets from the cell we're on. So in other words, how do I get to a neighboring cell from the cell I'm on? So let's say if we are at position ij, so imagine board I subscript j, then the one to the left and above that is going to be I minus 1, j minus 1. The one directly to the left of that is going to have an offset. The one to down and to the left is going to have an offset directly up. In other words, there are going to be 8 different ones of these offsets around where we are. But one thing to note is do not count the neighbor cell itself, or the cell itself as a neighbor to itself. In other words, never look at ij because it is not a neighbor, it is itself. So just make sure you have that in your logic. One other thing to note here about this is make sure you don't go off the end of that array, because remember that in C, things are stored contiguously. There's no bounds checking on arrays. So if you accidentally do not take care of the case where you go one row off the bottom, then you're going to be off in memory that's not allocated to this array and your program could crash. Also, if you're not dealing with that with the columns correctly and you go off of one of those, since it's contiguous in memory, it'll wrap around to the other side. So make sure you handle that case where you're not going outside of the bounds of how many 0 to the number of rows minus 1, 0 to the number of columns minus 1. Make sure you don't leave that space. And make sure you don't count the cell as a neighbor to itself. Okay, next state, and I have no idea why this thing decides that I don't need underscores in here. Oops. All right. Okay, so the next state function, what that's going to do is you're going to pass the entire board in again, a pointer to the board array, and you're going to pass an xy, and that function is going to return either a 0 for dead or a 1 for alive for that particular cell. So in other words, what we're going to do is when we call this function, is it basically says, hey, is this cell going to be alive in the next generation, or is it going to be dead in the next generation? So I would suggest, again, using something like 0 for dead, 1 for alive. I would also suggest that that function call the num neighbors function and then use the return value from that, along with the current state of the cell. Is it currently dead or alive, in a set of if statements that model or mirror the rules for the game of life. And then use that to determine the value that this returns. So this function is always going to return either a 0 saying it's dead or a 1 saying it's alive. But it's going to be based on the rules and what it got back from the num neighbors function from calling that. So again, look at the game of life rules and think of if statements for each of those rules. If this is true and this is true, return a 1. If this is true and num neighbors returns this, then return a 0. So just think about how those if statements would work for each of those. Okay, the next generation function is you're just going to pass the board to that. We don't have to pass an x and y because it's going to iterate through every cell in the board. So every row, every column, or every x and y, every I and j, however you want to think about that. So think about how you did that with your display board function first, because that has a nested loop that's going to go through that. And not just that, but make sure that for every one of those cells, you're going to call this next state function on each cell. But one thing to note about next generation is that you need to make a copy of the board. So we don't want to go through and change it as we're going through, because that would affect the results. And if you look back at how we did that in the original one, we went through and we looked at, okay, which things stayed alive and which things stayed dead. And then after we make that entire new board, we need to copy that back over the original. Now, how do you copy it back over the original? There's a couple ways there. you could do that. You could make another nested loop after you generated all of the state of the next board and just copy that entire thing back over. Or I'm going to give you another hint that's not listed here. There's a function called memcopy, MEMCPY, that I would look at. It's a standard library function, but what it does is you give it a pointer and another pointer and how many things you want copied. You might think of, well, size of would be great to use for that. But you give it a pointer to the destination, a pointer to the source, how many bytes to copy, and it'll copy the whole thing for you without you having to make a loop to go through all of them. Now, after you have that function working, you're just going to call that in main inside of that loop. It basically does next generation, get input, or next generation display board, get input, next generation display board, get input over and over again. So your main function for this program will be really small. There won't be a whole lot to it. But the functions for the other stuff will also be pretty small. There's not a lot of code that you need to write here. The hardest one is probably going to be this next state, or maybe num neighbors. Those two are probably the hardest ones, but they're really not that bad. And again, the board is going to be passed in as a two-dimensional array in this, so that the function can change it. Okay, a couple other items is I want you to use pound defines for the board height and width, so it can be changed easily, and just do a pound define board height 25, pound define board width 25. And that way we can try different sizes. And one thing that I would suggest doing, or that you need to do for this lab, is put the pound defines and all the function prototypes in a header file as we described in class. In other words, make a header file called like gameoflife.h, stick all the function prototypes for every one of these functions in there, stick, except for main, and stick the functions in a .c file, the actual implementation in a .c file. And that way when we're in the future, because we are going to do another lab in the future where we're going to use the same thing, that way you could reuse this code for some other program later on by just saying basically pound include the gameoflife.h, and then you could call any of those functions whenever you want. And another thing I would suggest is for troubleshooting your program, making it sure it works all right, you can change by pound defining these rather than hard coding everything everywhere. You could just change them to like 5 and 5, and then get a 5 by 5 grid, which is easier to kind of mentally trace through and make sure everything is working correctly. And since this lab requires us to understand and use multidimensional arrays, let's take a quick trip down memory lane and look at how those work. All right, so multidimensional arrays. So in other words, in this program, we're going to make a multidimensional array for character. It's a type character. But remember, to make a multidimensional array, to declare it, you would say, like, for example, in our case, char, give it a name. In our case, board. And then here you might have it be num. Well, you'd put the dimensions in. In our case, since those are pound defined, it would effectively be like 25 by 25 based on what gets substituted in for those. And we can initialize that to be all zeros when we create it if we want to. But one thing that I want to point out here is this is like what your main program is going to look like. You're going to have, like, for example, char, board, then the 2 pound defines in here, which effectively make 25 by 25. And then what we're going to have is then a call to the function for init board, and then our loop that goes through, and inside the loop we're going to call display board, next generation display board, next generation display board with getting input, and we're going to have that loop continue. And the only way to break out of that loop is if they type Q or exit rather than just hitting enter. Now, we need to pass that board array to a function. So that function is going to have to receive a char board array that's the same size. So again, those pound defines for the columns and rows are going to go in here. So effectively, we're going to get 25 by 25. And then inside the function, we can access that just like it's a two-dimensional array because we have a pointer to it down here. Now, one thing to keep in mind is you can, when you declare these functions, you can leave this part blank. The first one can be blank so you can specify it or not. Doesn't really matter, but it needs to have the second one specified. The first one can be omitted. But for clarity, maybe just put both of them in there. Now, to pass multidimensional arrays, we actually just talked about that. And so here we are passing it. This is what your function is going to look like, except this is going to be char. That's going to be board. Although you can name it whatever you want. And then you're going to access it. Now, notice in here, this is the reason I included this example is because this shows us going through every row and every column. So there's columns. This would be rows. And that's what you're going to need to do for your draw board function. That's what you're going to need to do for your next generation function. So keep in mind that this is the kind of thing that you're going to need in those codes. So take a look at that as an example. Okay, so that's all for today. You should have enough to get working on that lab. What I would suggest doing is, again, work on it one thing at a time. For example, write a main program, write the init board function, get that to compile, write the displayed board function, get that to compile, in your main function, make it call init board and display board, make sure that works. You might also make sure to put an srand with time in your init board at the top outside the loop. And that way you can make sure that on different runs you get different board setups. And then once you have that working, add NextGeneration and num neighbors and get all of that working together. And then maybe call display board, run the NextGeneration, call display board again, and then see that it's different. Make sure that it makes sense. Also on a 5x5, you can mentally look at all of it, visually look at all of it, make sure that what you're getting as the next generation makes sense, and then change it to 25x25 and add the rest of the logic. So essentially just develop the program, work on it a little bit, get one thing working at a time. And I'm a big proponent of kind of that iterative development process rather than trying to write all of it out at once and then having things go wrong and not knowing where it's going wrong. Get one thing working at a time, test each of those things, and then evolve your program or grow your program into what it needs to be. Okay, so that's all we're going to cover today. Again, make sure to work on this lab. Next class, we're probably going to have a chance for some bonus points, and there also is going to be another lecture next time, but I'll send an email about the chance for the bonus points. I'll be sure to send that, and make sure to do your civic duty and vote. And while doing so, make sure to stay safe, wear a mask, stay away from people as much as possible. That's probably a general good rule of thumb for life in general. Stay away from people. But anyway, do start working on the lab. And if you have questions or problems, shoot me an email, send me a text message. Let me know. We can always jump on a Zoom, or I can come down and we can talk about it. Also, make sure to register for classes. All right, that's it. So let's stop there.